Ryan, do you remember what energy is? Remember what the definition for energy is? Good. Energy is the ability to do work. Now, that doesn't mean that energy is doing work right now, but it means it has the potential to do work. It has the potential to do something. In other words, it has the potential to make something move, right? Now, we got two kinds of energy. There's potential energy and there's kinetic energy. In general, potential energy is what? Not specifically the type of energy, right? But in general, potential energy is what? Ryan, was your hand up there? Good, it's stored energy. So it's not doing something right now. It's not doing work at the current moment, but it has the ability to do work, has the ability to cause something to move down the road. So it's stored right now. It's waiting to do something. Ryan, what's the one example of potential energy? Good, gravitational potential energy. And gravitational potential energy is defined as what? Good. The equation is EP is equal to mgh, but we define it as energy, stored energy due to what? Due to an object's, Kevin, what's gravitational potential energy due to? Stored energy due to an object's gravity? Yeah, kind of, yeah. Height, yeah, due to an object's height. So gravitational potential energy, stored energy due to an object's height above the ground. What's the other kind of potential energy that we looked at? Jordan? Yeah, good. Spring potential energy or elastic potential energy. And that's potential energy stored due to what? In displacement? Yeah, let's be a little bit more specific though. What kind of displacement? It's stored energy in a spring or an elastic that's stretched or compressed. So a spring or an elastic that has a displacement. Not the typical kind of displacement that we think of, the movement, right? When we throw something, not that displacement, but the stretching or compression. The equation for elastic potential energy was 1/2 kx squared. We'll deal with that a little bit more in a minute because that's what our homework was on last night. Kinetic energy, well, there's only really one kind of kinetic energy. Anything that's moving has kinetic energy. And the equation for that would be 1/2 mv squared. One quick question with that, and then we'll go into the elastic potential energy stuff. What's V stand for? What's V stand for, Alana? Good. And speed's going to be measured in what units? Meters per second. Good. If we have, let's say, 72 kilometers per hour, we need to convert that to meters per second. How would we go about doing that? How do we go about doing that? Okay. All right, so 72 kilometers is 72,000 meters. 1 hour is 3,600 seconds. So it becomes 72,000 divided by 3,600, which would give me 20 meters per second. What if it's to the west? What if it's a negative value? What do we plug into our kinetic energy equation if it's a negative value? Do we put in the negative? No, why not? Good, it's 1/2 m speed squared, not 1/2 m velocity squared. Good? All right, this is what we really have to focus on for the homework that we had last night. Elastic potential energy. Of course, that equation was 1/2 kx squared. X stood for, Carrie already alluded to this, it was the displacement. Again, the displacement is not how far the object moves, but rather how much it's stretched or compressed from its equilibrium or its natural position. The units for that are going to be meters. K is defined as the spring constant or the elastic constant. What are the units for that? Jacob? Good, newtons per meter. Now, the one thing you have to be careful of with the spring constant, and we encountered this in an example problem yesterday, and I think you did in the homework questions as well. The spring constant for a spring, for a certain spring or elastic, is the same. It doesn't change. So we encountered that question yesterday where we found the spring constant, and then we stretched it a different amount. And everybody all of a sudden thinks, oh, we got to calculate a new spring constant when we stretch it a different amount. No, you don't. When you stretch it a different amount, it has the same spring constant. It just has a different force. Now, sometimes we've got to calculate that spring constant. We've got to find it some other way so that we can plug it into there. Do you guys remember what equation we would use to calculate the spring constant? It's called Hooke's law. Aiden? Good. K is equal to F over X. Hooke's law. The force is equal to the spring constant times the displacement, where the spring constant is equal to the force over the displacement. So sometimes you got to get K here, plug it into this. Sometimes you've actually got to get K here and then plug it into this. But these are typically the two equations that apply when you've got one of these spring problems, right? Well, last night you had 5 of these spring problems. Questions 1 to 5 on page 301. Any issues with any of those questions? I know we're going to have number 5 because when I took a peek at who had it done, there were a few people that said they had trouble with number 5. Any others, though, besides number 5? Bruce? 3B? Lana? 4? 3, 4, and 5. Okay, let's take a look at 3, 4, and 5 then. You know what? We'll do all of number 3, Lewis, just so that we have the perspective for question B. Okay, number 3 it is. 3 says the elastic constant for a spring is 750 meters. How far do you got to stretch it from its equilibrium position? In other words, it's sitting on the table. Nobody's pulling it. Nobody's pushing it. That's its equilibrium position. How much do you need to stretch it from that natural position in order to store 45 joules of elastic potential energy in it? Well, we got a spring constant here of 750 newtons per meter. Remember that what do we say that the value of the spring constant is related to? The higher the value of the spring constant, the blank the spring. The lower the value of the spring constant, the blank the spring. Yeah, kind of. The stronger it is, the stiffer the spring is. A car spring, right, that almost holds a car up, right? The suspension of a car up has a really, really high spring constant. Okay, it's difficult to compress that. It's hard to compress it, but it'll store a lot of potential energy when you do compress it. Versus a pen, the spring in a pen, which has a very low spring constant because it's really easy to compress that spring. This one's 750 newtons per meter. We've got 45 joules of potential energy stored in there, 45.0 joules. We're looking for, what are we looking for here? What variable is it? K or is it X? Tony? Yeah, we're looking for X here. And again, we're looking for that in meters, but we got our units here in these other variables in standard units. So we're going to get standard units out of this automatically. All right, what equation do you want to use? F equals Kx, that Hooke's law thing? Or do you want to use this new equation that we learned yesterday for spring potential energy? Yeah, let's say EP is equal to 1/2 Kx squared. Now, the only challenge with this is rearranging it to solve for X. That's not too bad though, right? Get rid of what's not attached. Is there anything that's not attached here? No, there isn't. Lewis says, shaking his head, no. Everything's attached. So let's get rid of what is attached. The 1/2 K is multiplied by X. How do we get rid of the 1/2 of the K? Derek? We divide it. So let's say EP over 1/2 K. Now, you could have taken the 1/2 over a different way. What's the other way we could have done that? Yep. Yeah, instead of dividing by 1/2, we could have multiplied by 2. Exactly the same thing, right? How do we get rid of that squared on the X? Jordan? We square root it, right? So it becomes X is equal to the square root of EP over 1/2 K. Now, I see lots of people rearranging an equation like this for, say, K. You never square root it when you're solving for K. The only time you introduce a square root sign is if the variable you're solving for is squared. So the only time you're ever going to see a square root in this equation is if you're solving for X. All right, EP is 45.0 joules over 1/2 of 750. Okay, we square root all that. We do the math for that one. What do we end up getting for X there? Ali, you got that one? 0.34641 meters. Thank you, Ali. Ali's gave me the unrounded number, which is good. I'm going to round that to 3 digits here for a final answer. But but I want that unrounded number written down just in case I need to use it for B. 3 digits would be 0.346 meters. All right, now if we wanted to double the elastic potential energy, how much further would we need to stretch it? Oh, good question. If we wanted to double the potential energy, how much further would we need to stretch it? Well, what's my potential energy now in question B? We'll do B in green here so we can distinguish it. Let's write down some givens here. What's EP for question B? 90 joules, right? It's double. It's twice as much. 90.0 joules. What are we looking for here? X, right? K is the same value because even though we're stretching it a different amount, the value of the spring constant doesn't change. Same thing, right? Almost. X is equal to the square root of EP over 1/2 K, or we could say 2 EP over K. We get 0.489898 meters. Louis, is that what you got for question B? You asked me for 3B, right? Yeah, that's what I get there, but that's not the answer. What do we got to do? Lana? Good. Why do you subtract the final and initial displacement? Good. We're not asked for how much it's stretched here. We're asking for how much farther we need to stretch it. So we're asked for the difference in the displacements here. So it's going to be 0.489898 subtract 0.346. That should give me my answer, which is, what is it, somewhere around 0.15-ish. Subtract those two numbers, tell me what you get. 0.143 meters, and I assume that's the answer that was given to us in our book. Yes? All right. Does that make sense? Again, listen, if you got this number, if you calculated this number, and this is a test question, is out of 4, you get 3 out of 4, right? You knew what you were doing, right? But if you're looking for a difference, if they ask you for that, then answer the question. Right? Subtract the 2 to get the difference. All right, let's take a look at number 4 here now, right? A spring has an elastic constant of 4.4 times 10 to the 4th. So that's a big one, actually. That's a big value, right, of K. What's the change in elastic potential energy stored when it stretches from 12.5 to 15 centimeters? So we've got two X's here. We've got an initial X of 12.5 centimeters, or 0.125 meters, because we got to be in meters here, right? 0.125 meters. And then we got a final of 0.150 meters. We want to find delta EP. Can I do this? Can I say delta EP is equal to 1/2 K times delta X squared? Can I do that? Why can't I do that? If I'm looking for delta E, and E is 1/2 Kx squared, then why can't I just say delta E is 1/2 K times delta X squared? Good. If X is squared, then you can't do that. If X wasn't squared, then that would actually work. But since it is, you can't do that. So let's instead get EP initial. Who's got a value for that? Zane, you got a value for that one? $343.75. Anybody else agree? Okay, good, thank you. Well, what next? Zach, what do you want to do next? Good, the final potential energy, right? And we find it in the same way, we just use the other number. So it's, again, 4.4 times 10 to the 4. Remember, it's the same spring. The spring constant isn't going to change. Times by 0.150. squared. We do that math, what do we get? 490 point, exactly. Okay. So now, let's see, who are we going to pick on this time? Jared, what are you going to do now? Yeah. Yeah, we're going to subtract them, right? So 495 minus 343.75 equals, what is that? 151.25 or 151 joules. Good. Did anybody try the whole 1/2 k times delta x squared? Anybody try that? No? Yes? No? Okay. All right, so we're good there? Let's take a look at number 5 then, our last one. This is the one that seemed to give people the most trouble. It says, when a spring is stretched by 0.4 meters from its equilibrium position, its elastic potential energy is this value. All right. So x is 0.400 meters, and EP is 500 joules. 5.00 times 10 to the 2. In question A, we're looking for the force required to produce this. We'll worry about B later on, okay? Let's do one thing at a time here. Tyler, you got an idea here? You got an idea as to what to start with? There's a couple things we could do first, so. Okay, so how'd you do that? You can actually, no, you're right. Yeah. Okay, good. EP is equal to 1/2 kx squared. Guys, remember what we've said a 1,000 times now. Everybody can start somewhere, right? Everybody at the thinking can start somewhere. You've got a potential energy. You've got an x. Okay, Tyler suggested, let's find the spring constant. So let's do that. Is that what we're looking for? No. Is it going to be helpful? Probably. But even if it's not, it's no big deal, okay, because it's not a wrong answer. It's a correct value. It's just not what we're looking for. Let's solve for spring constant here now and see what happens. We can take the half and the x squared over by dividing. We get EP is over 1/2 x squared equals k. Do we need to square root that? No, not unless we're solving for x. We don't need to square root that. So k becomes equal to 500 divided by 1/2 of 0.400 squared. What do we get for the spring constant there? Steph, you get that? Okay. 160, even? Exactly 160? All right. What next? Lewis? You get what? 6250. Okay. Okay. Anybody agree with that? Okay. Check that calculation, Carrie, okay? 6250 newtons per meter. So a pretty high value of a spring constant. What next? What next? Find, do you have an idea as to what to do next when you're finding the force given x, given F, or sorry, given K? Okay, we have K, so let's just rearrange that now and say F is equal to K times X. Looking for the force, got K, 6250, got X is 0.400. Multiply those numbers together, and what do we get? 2,700? Is that right? 2,500? Which should be rounded to 3 digits, so 2.50 times 10 to the 3 newtons. It's a bit of a tricky question, right? But we all know where to start. Okay, some of you may have said, well, if I want to find force, I got to use K times X. Great, start there. Some of you said, oh, I can find spring constant. Let me find that first. Great, start there. I don't care where you start. Okay, but everybody's got a place. Okay, no excuse for not having a place to start. B, if the force causing the stretch is changed to 1,000 meters, how much elastic potential energy, how much change in elastic potential energy results? So now what do we got? We don't have X anymore. We don't have EP anymore because that's changed. We have K. K is still the same for question B, 6250. Same spring constant. Now the force is 1,000 meters, sorry, 1,000 newtons. Idea? Where should I start? Tyler? Add 1,000 newtons to the force I had before. So say 3,500 newtons. No. That's okay though, that's a good guess. We're not changing the force by 1,000, we're changing it to 1,000. So let's not make the force 3,500. Okay, the force was 2,500, the force is now 1,000. Does that make sense, Tyler? We're not changing it by 1,000. Make sense? Those little words sometimes though, hey, like they mess us up sometimes, right? By or to, it completely changes the context of this question, right? We're changing it to 1,000 newtons, so F is 1,000. Any other ideas? Jordan? Is your hand kind of there? No? Okay. Okay, well, let's figure out X. Okay, so we got F and K. Let's figure out X. It's F over K. So it's 1,000 over 6250. What does that give me, Haley? 0.16 exactly? Okay, 0.16 meters. All right, good, good. What next then? Well, I don't think I've asked you anything here today. What next? Good. We're never going to try to find delta EP directly. We're always going to try to find EP and then subtract to get delta EP. So Leah's telling me that I want to try to find the energy here, 1/2 kx squared. K we have, it's 6250. X we have, the new X is 0.16. What do we get for that EP? Yep. 80. Okay. That would be joules, though, right? 80 joules. Anybody else get that? Yes? Is that our answer? No, it's not our answer. So what do we got to do? We're almost there, though, right? What do we got to do at this point? Yeah. Yeah, it's final minus initial. So we add, what, 500 joules? Now we have 80 joules. So the difference is 420 joules. That would be our answer. How many people got that? Okay. You feel better about it, those of you who didn't get it? A little bit of homework for tomorrow, Carrie. A little bit of homework for tomorrow. Page 305. Good news is, lots of questions on 305. You don't have to do all of them. You have to do 7, 8, 9, and 11. Okay, just 7, 8, 9, and 11 on page 305. You might have a little bit of time to work on that later on in this class. You might not. I'm not sure. Okay, we're not going to work on it right now. We got a couple more topics to cover here in this unit, and then we're finished up. We're going to look at the concept of work now, which is very closely related to energy. We define, in fact, energy as the ability to do work. Yep. So clearly work and energy are related to each other. Work we're going to define as the change in energy experienced by an object. So how much energy the object gains or loses. There's an empty desk at the front of the room here today. This desk has 0 joules of energy right now. 0. How can I change the energy of that desk? In other words, how can I do work on that desk? Well, there's 2 things I got to do. What's one of them? Yep. I got to move it. There's got to be movement. There's got to be a displacement. If there's no displacement, then the energy of that desk isn't changing. Well, how do I get it moving? I apply force. I push it. So 2 things that are required to do work on an object, which are the 2 things that are required to change the energy of that object. I got to push it, and I got to move it. A force and a displacement. So we're going to say that the work depends upon the force and the displacement, which leads us to the equation that we have for work. W is equal to delta E. W is equal to the change in energy, but it's also equal to F times D. Now, you see this a little bit italicized here. In order for this equation to be perfectly valid, W is equal to F times D, Seth, then the force and the displacement must be in the same direction. So in other words, when I push that desk, if I push it parallel to the floor and it moves parallel to the floor, then I'm good to go. But if I push it at an angle like this, like I am right now, and it moves parallel to the floor, or if I pull a wagon at an angle of 30 degrees and it moves parallel along the floor, then this equation doesn't quite work for us. If they're not parallel, then we got to modify this equation a little bit. We're going to tack a cos theta onto the end of it. What that essentially does is you push it at an angle of 30 degrees, or you pull it at an angle of 30 degrees. What that effectively does is gives you the x component of your force, right? You could break it down into x components and y components. Find the x component. The x component would end up being F cosine theta. So if they're parallel, then you don't need to use the cosine theta. If they're not parallel, then you got to use the more general form of that equation, FD cosine theta. Let's say we've got an object like this, doesn't matter what the weight of the mass of it is, and we pull it like this, and it moves along that axis. Which equation do we use, the blue one or the green one? Yeah, the blue one, because we're pulling it in the same direction as it's moving, right? And as long as we're moving it parallel, then we're all good there. Even if I had something like this, even if it was moving to the right because it just had a lot of velocity for whatever reason, but I was pulling it to the left, I would be slowing it down now, right? What equation would I use, blue or green? Well, I could use either one here, actually. I could use the blue one if I want, because they're still parallel. But if I use the green one, then I'd put my angle of 180 in there. What's cosine 180? Hit cosine 180 on your calculator. -1. So we end up getting the same value, right? Except a negative version of it. That make sense? What if I pulled it like this? Oops, that's not what I wanted. What if it's a wagon that I'm pulling like this at 30 degrees, but yet it moves along the x-axis? Which equation would I use here, blue or green? Yep, definitely green in this case, right? And that theta in the green one would be 30 degrees, right? Hey, what about this one? Here's a tough one. I'm pulling it up the hill. The hill's at an angle of 30 degrees. Which one would I use, blue or green? 70? I'd use blue. Good. Why would I use blue, Stephanie? Looks to me like I should have an angle there, right? So I should put in 30 degrees into the green equation, right? You're right, though. I do use blue. I don't put an angle in there. Why not? I'm sorry? Yeah, good. If I'm pulling it up the hill and it moves up the hill, then I'm pulling it in the same direction that it moves, right? It's irrelevant what the angle of the hill is at that point. Does that make sense, guys? So we'd use that blue equation for that one, right? The specific form when we're pulling it parallel. All right? Where are we? There. Let's take a look at an example here on 294. It says we got a force of 150 newtons acting at 0 degrees, so this is 150. But the object is moving at 25 degrees here, 25 meters at 25 degrees. For whatever reason, right? It was moving that way already, and we're pulling it in a different direction. Whatever. Doesn't matter. We're pulling it one way, it's moving another way. What's the work done by the force? Blue equation or green equation? Let's go back to that one for a second. Blue or green? We're pulling it this way, it's moving this way. Blue or green? Yep, definitely going to be green. We're pulling it one way, it's moving another way. It's not moving parallel to the way that we pull it, so we're going to use the green equation with the theta in there. Becomes W is equal to, well, we could say W is equal to delta E, but we don't need to here because we're not looking for the change in energy. Just say W is equal to FD cosine theta. F is 150, D is 25, and theta is 25.0 degrees. We end up getting for that 3,398.65. What would the units be? Oh, good question. What would the units be for that? Carrie? Say that again. Stop. No, go back. No, go back. Stop. Oh, I didn't stop you quick enough. What are the units? Joules. Right? It's energy. It's a change in energy. Energy is joules, work is joules. We're going to round that, by the way, to 3 digits. 3.40 times 10 to the 3 joules. Hey, by the way, would work be a vector or a scalar? You guys know this. Energy is a scalar. Work is a, no. If work is a change in energy, and energy is a scalar, then work has got to be a scalar as well. Yeah. Okay, that's not so bad, is it, Stephanie? Okay, good question. Good question. Why is there a vector sign over F and D if work is a scalar? I'm sorry? For kinetic energy? Yeah, yeah. But here, you guys probably haven't done this mathematically yet. But at some point you will. I'm not sure if it'll be in Math 30 or where exactly you see this, but when you multiply a scalar by a scalar, you get a scalar. And you do vectors and scalars in math at some point, if you haven't already. Scalar by a scalar gives you a scalar. A scalar by a vector gives you a vector. But when you multiply a vector by a vector, you get a scalar. So here we got 2 vectors that we're multiplying together. We still get a scalar out of that. So it's okay to have those vectors in there. If we had one of them, then that would turn it into a vector. But 2 of them leaves it as scalar. Okay? I'm going to give you a couple minutes, guys, to work on, let's say it's just questions 1 to 3 here right now. A couple minutes to work on questions 1 to 3, and then just before the end of the class, I want to do one more example with you, okay? All right, one last example here. This one's not in your book, so you're going to have to, unfortunately, copy out the question. It says a 20-kilogram object gains 300 joules of kinetic energy as it's pushed a distance of 100 meters. What's the force used to push the object? This, when you look at the question, when you read the question for the first time, may appear to have nothing to do with work. We gain 300 joules of kinetic energy. We're pushing it 100 meters. What's the force? It doesn't mention the word work once, but it does mention a gain of energy. How did we define work again? What was the definition for work? Allie, what was the definition for work? Good. Good. The change in energy experienced by the object. If this object gained 300 joules, then what was its change in energy? Derek? 300 joules. Then what was the work done on this object? Good. So the work done in this question is 300 joules. We've got a distance or a displacement of 100 meters. We want to find the force. So it's a question that isn't really any more difficult than the ones we've been doing. In fact, maybe easier because there's no angle involved. We just have to recognize that the change in energy here, 300 joules, is equal to the work. So it becomes W is equal to F times D. Let's rearrange that to solve for F. And it becomes W over D. The work is 300 joules, and the displacement is 100 meters. That gives us 3.00 newtons. You got that? So same type of question, slightly different terminology. Ladies, slightly different terminology. That's it. All right, so your homework for tonight is those check and reflect questions that I assigned on page 305. It was 7, 8, 9, and 11. In addition, you have page 294, number 1 to 3, the questions you were just working on. Okay? That's it for today, guys.